So I'm gonna do this a little bit more interactively. Please feel free to ask questions as we're going through. I will do my best to answer them as well as I can. This is a newer area of YT for me, so I'm really excited to be talking about it with you today. So in this particular lesson, we're going to be talking about data selections, and you got a little bit of a preview with this when Matt was doing his last tutorial. So we're going to look at how we explore some attributes of fields and like some preliminary analysis we can do on fields. And then we're going to talk about different selection routines that we can do in both volume and filtering and things like that. So we're going to be using a different data set that was used in the last tutorial. This is Enzo Tiny Cosmology. I am not an astro person by training, so I don't know if anybody else wants to describe what this data set is simulating. It looks cool, which is why I chose it. Okay, so now we can see YT has some given us some information on our simulation, just like we got an isolated galaxy in the last tutorial. Let's look and see what fields are available to us with this particular data set. Okay, so we have some similar things that we saw in the last one. In most of this tutorial, I'm going to be going with temperature and density, but there's going to be some exercises that you can do later on, and you can use any one of these fields that you'd like to while you're doing those exercises. We can see that there's quite a bit available to us. So in the last tutorial, we talked a little bit about that ds.all_data selected the full domain worth of data. And so I'm going to do that again, and we're going to call it DD, and then I'm going to do another analysis on it by looking at the quantities, and I'm going to use Extrema, and then I'm going to do that Extrema selection in density and see what happens. Okay, so what this returns is an array of both the minimum value of density in my entire domain and the maximum value of the density in my entire domain. And we can still do unit conversions with this because it's a unit array. So we could do something like, let's see here, I'm gonna copy this and we can do something like, it's in units, right? And then we can say, and we can change it just like that. Okay, so we've done a few things, like I mentioned. We have our full YT region, which is DD. And if we look at that, we can see it's a YT region object. And the center and extrema, the right edge and the left edge, are returned in centimeters. However, we can look and see what other quantities we can look at with this selection. So let's look at the other quantities that we can do. I did Extrema up here in cell 4. Let's see what else is available. So there's a weighted average, there's a total mass, center of mass, bulk velocity, and like we were looking at Extrema. And so there's lots of different things that are available. Let's see what happens if we look at the weighted average quantity function and what is available with that. Okay, so what weighted average quantity is looking for is a field. And so this is the field that we want to do the weighted average quantity on. And then we can choose a weight field, and that's a string or a tuple. So we can do weighted average with temperature, density weighted with temperature. We could also do it with something like ones, so that way it's all, that way it's not weighted completely, but, and so this will update quite quickly because we have some optimized functions with that. And we can also pass a list of fields and we can weight all of them the same way. So we could do density and temperature and find the temperature weighted quantities, the temperature weighted average on both of those. and then we'll get those, and we have some sane units of those. Okay, so I have some exercises in here. We're not going to do them now, but later today I will be available and we can talk through them if you want. I'm going to have you be doing these exercises with a different ENSO cosmology data set. So this is ENSO Cosmology Plus. And so I want you to try and kind of experiment with these different quantity values and try and weight instead with the cell volume rather than temperature, and kind of explore and get some intuition to that data set with these particular quantities. Okay. So also in the last tutorial, we saw that there's this ds.r selector that Matt showed you, and this ds.r. And we can do it like with density or something. Everybody, I don't know if you all have this experience, but every time I'm typing in front of people, I make a typo. Every time it happens. We can do ds.r with density. What am I doing wrong?
You might need square brackets, maybe?
Is that right? No, I think. Let me think here.
It's square in your tips right above.
Oh, is it? Oh, it is. Yep, you're totally right. Wow, I should read my own tips to myself. So we can do something like this ds.r. And this is going to return a flattened array of the density value, and if we can, of the density field, which is the same thing as our dd. So dd, again, is ds.all-data, and if I do dd density, it's a unit array of the same thing. So we can access data in a similar way, but we have different pathways to do it. ds.r is a really nice way to make a region selection really quickly. And so ds.r, like Matt showed you, you can do things like select the entire data set, right? Like this. And then we could do something like that, and that's a YT region as opposed to this flattened array. But then if we did DE density, it's going to look the same as our other ones. So ds.r is a very shorthand notation for a region selection. In most of this tutorial, what I'm going to be doing is using the really explicit function calls as opposed to using ds.r, but later on we might use ds.r a little bit. But I wanted to kind of explain how you can take the same path with ds.r as you can when you're doing some of these other region selection options.
Ari has a question for you, Marikan.
Yes, Ari.
Yeah, this is a high level question, and it may not be interesting or appropriate, but
that's fine.
So usually the fact that this is square brackets would imply that this is a data object that hangs on the object and not a method that's providing a functional interface. Is that the correct interpretation, and or is that a choice that was made to express this?
I am not positive. Matt, maybe you want to answer this one?
Unmute, unmute.
Sorry, I have both hardware and software mute. Am I still muted?
No, you are. We can hear you.
This was set up to imitate the mgrid object in NumPy, which lets you just sort of select between different regions or select between different spaces inside the number line. So it's supposed to look kind of like that, but it does on the back end call some functions. But the idea is that it's supposed to look like an mgrid or like an iLocation in pandas or something like that.
Okay, thank you, Matt. Does that answer your question, Ari?
Yeah, that's great. Thanks a lot.
Yep, no problem. Okay, so now we've kind of looked at some of our some of the quantities we can inspect with our field. And we did this on our all data, right? With looking at the Extrema. Now let's try and do some volumetric region selectors. So we kind of already did a volumetric region by selecting all data, but we can also use some of yT's built-in functions. So this next one I'm doing is ds.box. And again, this is explicit. You could do something like this with ds.r, but I'm going to show all of the explicit sort of shape objects, shape function calls, so you can see them. So, so we can do ds.box. And then let's look at box, bx, and see what it looks like. And it's a yT region object. And this particular ds.box, I did select the full region. And in this particular, so this is like the left, the bottom left edge, and this is the bottom right, like when I'm choosing the ds.box, but we can actually look at this function call. And you can see that you have a left edge and a right edge that you're specifying. But here I'm doing this in the domain coordinates rather than, so like when we're looking at the box object, it says the center is in centimeters. And then the right edge also is specified in centimeters. But when we're doing in domain coordinates, it's generally from 0 to 1 and normalized. So this way we can kind of quickly get an idea of the full data, or we could select like half of the data very quickly by using these domain coordinates. So that's what I'm doing here with this ds.box. Okay, so we have a yT region object. Let's look again at our DD object. So I told you before that what DD did was this ds.alldata, and I selected all the data in my domain. So does it look the same as box, since I decided to use the full domain width with box? At first pass, it looks basically the same. It has the same left edge, right edge, and center. Let's look at some of the quantities that that are available on each one. So let's compare box and DD. Okay, so our temperature extrema look the same. How about this weighted average? Let's see what that looks like. Okay, so I mean, I'm just gonna assume this is basically the same. I've created a box that spans into our domain. That's also what ds.alldata is doing. So let's try and do a region selector instead with a sphere. So before we saw a quick preview of sphere. So if we're looking at the doc string here, we can see it is requiring a center point, and it also wants a radius. And then you can do some other things like data source, which I'll get into a little bit later. Okay, so we have this ds.sphere. Let's try it. I'm going to make a center point at the midpoint of the domain, so at 0.5, 0.5, 0.5, and I'm going to make a sphere with a radius of 0.25 with the sphere object. Now let's take a look at it and see what happens. Okay, is my center point the same as what I saw before? Yep, it is the exact same center as my yT regions. So this is definitely at the midpoint, and I have this radius spanning out, which is 0.25 of my domain. Now I can kind of compare some of the quantities between my sphere and my full domain and see how some of the properties of my data set have changed now in this particular selection object as opposed to my full region. And again, yT sphere is, you can do similar operations on all of these volumetric data selections. So you saw before that box and ds.alldata are returning a yT region object. And this is a yT sphere. Those are both subclass from the same selector class. So you can do a lot of the same operations on all of them, even if they geometrically look a little bit different. Okay, so let's compare some of our quantities between the two. So, okay, we can see that there's definitely different densities. different weighted averages based on the volume, and different means as well, right? And so here I'm not actually doing, I've like revealed something here now. So I was accessing these quantities methods on my region selector objects, right? And that's with the extrema and the weighted average. But here I accessed a new thing that's outside of the quantities interface, and that's this mean value. So let's take a look and see what mean does, because maybe it's a little bit more interesting. Okay, so we can compute the mean of a field, but we can also do something along an axis, which will return maybe not a single value based on the mean of my field. If I specify it along an axis, instead I will get mean of the field along that axis. And so it'll be like a two-dimensional representation of the average mean along that axis. And so let's see what that looks like. Okay, so instead of me getting a single value like I did up here, right, which is a single point, I now have a projection. So that means that I am getting like a new type of yT object return using the same interface. And so I'm going to get a little bit into projections a little bit farther down, but this is kind of a preview of what this is looking like. Okay, so now there's another exercise here. When you get to it, I'd like you to kind of choose a different region than the ones we've seen in your ENSO Cosmology Plus data set. Try and select maybe a disk or an ellipsoid or something like that in this new data set.
Quick question.
Yeah.
So when you use the access call, it makes it clear that the fields that would give sensible results are only grid fields. Is it that you could be using particle fields and it will simply fail if it's not a reasonable request, or never particle fields? Or are we only talking grid fields in this case?
It should work with particle fields.
And if you give it an axis, it just
it will project along that axis.
decomposing the particles into the cells?
So it will generate a pixelization. So I'm going to get into this in detail tomorrow, but the projection operation on particle fields is not independent of resolution. And so it assumes a given resolution, and then you can adjust that later on.
Okay, but it does a particle projection. Okay, thanks a lot.
Yeah, sorry, I'm sorry for talking over you, Madikin.
No, that was great because I did not know the answer. So I have not dealt with particle data in yT yet, so I really appreciate you answering that. That was great. Okay, so now we've seen a sort of volumetric data selection using our data set, but yT also can do data selections that are non-volumetric as well. So we can choose things like rays and slices. So let's see what a ray would look like. And let's first look at the doc string for ray. So what ray will do is create a 1D or like a line through that goes between two arbitrary points that you specify. So you have a starting point and an ending point. And then it'll return that, and so if you just pass the whole data set, it'll give you the values along that line of every single field. So let's try to create an arbitrary array based on our data set and see what that looks like. Okay, so we have our yT ray object. Now let's try and plot it. I'm going to try and plot it with matplotlib. So I'm going to import pyplot. And now T is the time sort of that the ray enters each cell that it's going through. And so that's what I'm plotting against with each of these values. And then I'm going to get my density data and my temperature data, and I'm going to make 2 different plots with it. And I've kind of mislabeled the x-axis here, but so we can actually see and inspect our field values along this arbitrary line. So this is something that would be really nice because we can kind of choose an arbitrary direction through our space, and you can get some intuition of how your data is behaving using ray objects like that. And I hope you all like Frankie Goes to Hollywood, because that's what that title is for. So it's great. So we can also do the same sort of quantities inspection with this ray object that we did with the volume objects before. So like we can look at the extrema in density and temperature with them. And we could do other things too, like, let's see. I'm going to look and see which ones we have again. Oh, yeah, we could do like max min location or something. And so we can get the min location and it'll return that for us based on our array, which is pretty cool. But we can also create 2D data objects. So I kind of gave you a little preview of this with this mean before, but we can create a slice, which is just a 2D slice through our data. So let's look and see what that docstring looks like. So again, we want to choose an axis that we're slicing along, and then you can choose our coordinate also to slice along. So I'm going to do a Z slice in our data set at 0.4 in the domain units. And let's look at what slice 1 looks like. Okay, so I can see that it's along, and so axis YT, you can pass a numbered axis or a string axis, and it will do either one. So this is like XYZ, so it's 0, 1, or 2. So I sliced in Z, so it's with axis 2. And we can again do the same sort of inspections that we did before with this particular object. So we can do the min, the max, and the mean, and calculate those on our slice object. We can also do things like off-axis slices. So I sliced along the Z-axis, but we can create a cutting plane. And so that we choose like a normal, we choose a normal vector that we are cutting out of, and then the center point that the cutting plane is going through. And so I had created a cutting plane here, and I'm also, instead of doing specified starting point, center point, I'm choosing a min. You can do min, max, or you can specify a coordinate. So I'm going to be doing a cutting plane with a normal of 2, 3, 5, and it's at the minimum value in my data. Okay, and so here's my min value, and let's look at what slice 2 looks like. And so instead of it being a YT slice, like the slice 1 object, like we saw before, this says YT cutting plane, and that's because it's like a separate type of object because it's an off-axis slice. But we can still do the same sort of operations, looking and inspecting each of these slices. And so again, we can do lots of cool sort of operations on our data that tell us a little bit about like what we can inspect the fields in our data by using these different selector objects. And these selector objects, I've only so far talked really about geometric selections, but in a little bit, we're going to talk about things that are a little bit outside of the geometric selections as well. Okay, so then I have another exercise for you when you get to it. And I want you to create an array object with the min and the max values. And I want you to find the locations of those values in this Enzo Cosmology Plus data set. And then I want you to create a slice object at whatever location you feel like in this data set. Okay, so now we've seen some slices, but we still don't know really what our data looks like. And a lot of these slice objects have plot methods on them to kind of give us an idea of what we're looking at. So we can do slice.plot, and then I'm just doing a show on here because it doesn't get as, it doesn't accumulate more. So this is, I wanted to plot just the density field of my first slice, which is again at 0.4 in X. So this is going to be a Y, as it's 0.4 in Z, so this is a YX plot. So we can see what our density looks like at this particular thing. We can also plot something like temperature with this plot method. So we can access different fields pretty easily with our slice object that we already created. And I don't know why these are adding. Does anybody, Matt, or I don't know, but.
Yeah, I think that what happens is that it overrides the display method as well as returning it.
Oh, okay.
It might go away if you put a semicolon at the end.
Of the.
Yeah, of the show.
Of the show? Okay, let's try.
No.
No. Well, it might if I refresh, I guess, because now I don't know. Anyway, yeah, sorry, everybody. I don't know. Anyway, so, but we can do some more advanced data selection as well. So right now you've seen these slice objects, just in a particular, through Z, but we can use a sphere and we can pass that as a data source in a slice object. And then we can plot this special slice that is only using a part of our full data set. So when we do our slice and we just do Z in 0.4, it's using the full data set domain, but we can also specify just a subset of the data, and that's what the data source keyword argument is doing. And so now I'm going to create a sphere in the center of my domain that extends out to 0.4 of my domain. And then I'm going to do a slice on that and use that sphere as my data source rather than the full data set. And let's see what that looks like. And then let's have the semicolon here. Okay, so now we can see this very specific version of our data that's using the sphere as our data source. And so, we can make some cool art that way, I suppose, right? In addition to doing cool science. We can even chain together volumes and do unions and plot that. So I'm going to create two different spheres, and their center points are not at the center of my domain. I've kind of made them slightly kitty corner from each other and with different radii. So that's sphere 3 and sphere 4. And then I'm going to do a union of those two spheres. So that's going to be joining them together. That is the additive. So this and this. And then I'm going to use that particular union object as a data source for my next slice. And I'm going to plot that. Okay, so now we can see these two different ones. If instead we wanted to do an OR, we could do, I just forgot what it was. Let me think. Hold on, you're just gonna have to stick with me for a second. I think it's an intersection. There we go. And so instead of being the two next to each other, I'm doing an or selection. So, or I'm doing like where the two are together, but not where they're apart. So, yeah, so this is kind of nice. You can then select very specific objects if you want to. You also don't have to join the same type of object. So I've just done a simple thing with ds.sphere here, but you could do this with like an ellipsoid and a sphere, or a cube and a sphere, or like 3 cubes randomly if you feel like it, whatever you want. And so this chaining together, I think, is very fun. And so for the next interactive exercise, I want you to create a slice object and temperature. And if you want, as a bonus, create an intersection with another volumetric object. You could make a new one, or you could use the one that you did in exercise 2 or 3. I can't remember which one. And then I also have a challenge exercise, which basically chains all the stuff together that we did so far in this tutorial. I want you to create this intersection object between a disk and a sphere at arbitrary locations. I want this to be the intersection, not the union, but you could do the union if you feel like it. And then make a slice object at its midpoint and visualize it with the dot plot method. Okay. Now, we've kind of talked a little bit about these basic slice objects, but I showed you a little bit before that we can do something like d.mean, right? And then I can specify something along an axis. So what this is going to do, so let's see. And then I'm going to do, let's see here. Okay, so I can also do the plot method on this object P1, which is this projection object. This is also a 2D object because I've projected the data down along the z-axis. So I can also do P1.show the same way. No, plot, sorry, not show. And so this is now my density projected along, projection, but it's like the mean of all of my data along the z-axis. And so it's a special type of thing. But we can also do something like we can do projection objects. And so projection objects take a field and you can project along an axis, and then you can choose a weight field, and you can also choose a, where's the thing I wanted to say? Yeah, then the method can tell us what type of, the method of integration that we're going to be doing, or the method of projection. So we can do an integration, or we can do a sum, or we can do the maximum intensity. So let's try that with one of these. So we'll do a density projection along X this time. And we'll do it as, and we'll do it as a maximum intensity projection. And we'll do this as, so this is the maximum intensity of my density field in X. And it was pretty easy to just like quick get the intuition of what that looks like when I'm plotting it. But I can also do the same thing with the data source that I did with the slice plots. So for example, I could do the same thing with this previous cell. And then I could do data source, I think it's SP1. let's see, that works. What was my sphere called? Oh, you know what we could call it? We could use the cool union object, but let's do sphere 4. And then I can do another selection with my, I can use the same type of data source object to filter out whatever projection data I want as well. Yeah, so this is all I have prepared on region selections. Does anybody have any questions about this so far? Is there anything that would be helpful? Okay, well, I am very happy to walk through some of these examples and worked problems with you in the afternoon session when we have a little bit more free time. I hope that this was helpful to you, and yeah, thank you for listening.
Oh, it looks like Matt has a question.
Oh, yes, Matt.
I was going to volunteer that you can also use the logical operations to generate the unions and the intersections and so on.
Mm-hmm. Oh, like the and, right?
Yeah, that might be something that you could show. Would just be, yeah.
Yeah. So I would do like SP3 and SP4, right?
Yep.
Yep. That's right. Yep. Okay. So I can do I'm gonna do a couple other ones in here. So I can do select 2, and then I can do the same. I'm gonna do the same filtering, but instead of data source, I'm gonna say select. Instead of sphere 4, I'm gonna use select 2. So you can see what that's gonna look like. Here we go.
And I think we've got or and not, which is minus, and XOR.
Ooh, okay. So I can do like this, right?
Yeah.
Let's see what that looks like. So did I maybe?
You did it right. It's just that now you'll see, since you're projecting.
Oh, right. Yes, because I'm projecting, it's a little bit different. Okay, maybe I'll do a slice then. Let's get rid of this and. Oh, I don't want to do a slice. Or do I want to have the access? Now I'm. Let's just see what happens.
Yeah, I think maybe if you just do the X, not the axis equals, or I guess I don't do dot slice, so I don't know.
Yeah, I don't, let's just see. Okay, let's just see. I have to check the doc string every time, basically.
Me too.
Oh, it's the other way around. X and then density. That's why it's confused. Oh, comma. No. Oh, no, I can just, no, it's going to assume I need the coordinate, not the field. And then I need to do, I can do P2 density. Oh. Can I do this? Let's see, how did I do it up here? Okay. Sorry, I'm scrolling all over the place, everybody. Hey, there we go. Cool, like crescent-y thing. Okay, I'm going to add this select to the same thing since we're going to play around with these operators. So we can do, yeah, so we don't have to use the union operators, like the explicit thing like I was doing. Like Matt's pointing out that you can use these logical operators that are built in. So we can do something like this. So this looks very similar to what we saw before. Then we saw the and, but I'll do it in the slice so you can see it not in the projection. We can do that. And then also there's like, I think we can do this one, right? Yes. Yeah, so were there any other logical operators that we could try out, Matt?
There's XOR, but you know, that's pretty limited use.
Okay, I'll leave it then. Yeah, but yeah, so you can chain a lot of these things together. So like we could also do like if we have multiple, if we added more sphere objects, we could chain, like we could do this plus this minus this, you know, something like that. So we can do lots of really fun sort of operations with it. And yeah, you can really, really finely choose and select your data with this. In the next tutorial, you're going to see a lot more about plotting. Like this particular plot method is very primitive compared to like using the other plot objects that you can do in YT. And I think Mike's going to cover that in the next particular lesson.
Can I ask another question about this combining regions? So I think in this tutorial, you've mostly talked about like volume-y regions, because I could also, I don't know who or if anybody is assigned to talk about it, but you can also select regions where your like density is above.
Yes,
10
you
to
can.
the minus 27 or something like that.
I think that's in lesson 5. It says filtering. That's like a filtering selection, and I think that's in the one right before it, the one you're doing.
Okay,
Yeah.
great. And then can I do the same operation on that? Could I say like, you know, sphere, like volume-y whatever region plus cut region based on density?
Yes.
Threshold?
Yep.
Yeah, cool.
Yep. You can
Very
chain
cool.
this together. So like you could do, like you can make your slice object, because you can pass like the, you know, include above and below on a slice method. So you could you create the slice with the data source of whatever volume object you're doing. So like your, you know, your sphere or something. And then you can modify that slice again with a include above or below or whatever you want.
Cool.
That's, I think, so that, so I was thinking about just showing a quick preview of this last night, but I think the include above and below, those easy accessors for that are not on the 4.0 branch right now. They're in master. And so they will be in 4.0 shortly, but we don't have them in 4.0 right now.
Okay, cool. Great. And Matt, your hand is up. I don't know if you had another question or if you just hadn't put it down or something. It's down. Never mind. Okay, cool.
Okay, well, I hope that this is helpful. And again, please feel free to ping me this afternoon. I'm happy to kind of walk through things. And at the very bottom here, I've linked to the documentation on each of these different type of YT selection objects. And so Stephanie and I were just talking a little bit about filtering objects with like this above and below value. But we've created some collections just now, and we've done geometric data selections in this particular tutorial so far. And so, yeah, I hope that this was helpful to all of you.